All right, good morning. Glad to be here. It's great to see that this AMD event is so well attended. So I'll be talking about a topic a lot of us are very, very interested in on efficient general intelligence. I want to emphasize on the efficiency part. The reason is that there's a lot of exciting progress on kind of how much of an intelligence we can get with the latest frontier models we have. However, we have to say that if you look at the efficiency, there's a huge gap. For example, we take some recent released model from DeepSeek because it's an open source model, so people did the profiling. And just do inferencing, it takes about almost 10 kilowatts. And then if you run it for 12 hours, that requires 500 megajoules. Right, human brain, and like you and I, that sitting here. So the brain works about 12 to 20 watts, and with 80 to 100 billion neurons. And in fact, my friends at the neuroscience correct me, says, no, not all these 100 billion neurons are responsible for intelligence. There's only about 16 billion neurons actually in the cortex that's actually for intelligence. So that actually runs that if you calculate in 12 hours about 500 kilowatts. So it can be kind of powered by 2 bananas. So the difference is huge, right? That's probably some of you had for the breakfast. So how can we bridge the gap? That's actually a very active research program we are doing at UCLA with help from the support from AMD. So 2 parts I'm going to talk about. One is on model innovation, and the other one is on platform customization that I will show you. So let's start with the model part. So I'll give you 2 examples. Each one I'll give 2 examples. The first one is about the hierarchical memory transformer. And a lot of intelligence comes in with these frontier models is because they have a very long context windows. So these days, it goes to about 1 million tokens that you can look at past. But that's also where the energy cost goes to because you do attention, it's a quadratic time operation. So how can we reduce that? So we was the first one, among the first one, come up with the idea of using long-term memories to reduce that. For example, I'm meeting with some of my AMD friends from university program. We met 6 months ago. And I'm not going to attend to every tokens that happened in the past 6 months. And then I'm just going to recall what's the last conversation, Ralph, we met in that April, right? So that's actually how it comes in, that you have a long-term memory, you have a short-term memory, you have sensory memory. So that's how human is structured, that in our memory system, you have this hierarchy. So this is actually what we want to do that in the large language model processing. So you can see that you have, let's say, information coming from the right to the left, that the middle one is the current segments. That's something we want to decode. So this approach can work with any backbone model, that can work with a DeepSeek model, can work with, let's say, a frontier model if we have access to that. So you first go through this model saying, what's the topic? The topic is the AMD Advanced AI Conference, and then you go to your past long-term memories to get the most relevant tokens out. And then, so those are the relevant topics, and then you have that comes in as an input together with your current input, and maybe plus something of the immediate past. So that form a new input, right? So look at, I'm not taking 1 million token that as a KV cache, I'm taking very relevant information from a long-term memory, and then go to the backbone model again, so then we can get an output. This output that we will output to the user, but at the same time, will actually be stored in the long-term memory, so have a new episode. So this approach is highly effective. For example, if you just look at using GPU L2 cache, you can store about over 2,000 long-term memory. So that's equivalent to 1.2 million context window. If you start using HBM, you can go to billions that context windows, or you use SST, is almost unlimited, hundreds of billions. So that's the approach we have. So we have a full paper of that. You can see the detail, but I'll give you some ideas. So if you look at it, is that GPT at that time, we submitted a paper, did the work 2 years ago, a 20 billion model. So we use a 3 billion model. And you can look at the context window. One is like 16K. We're using half K. And the result, summarization score, question answer scores, very competitive. In many contexts, we are better. So you can see that's actually leads to several X of a reduction, and 7X reduction on memory, and almost 2X reduction on efficiency, the improvement on efficiency. And you go to, let's say, at the edge end, let's say you look at the physical AI, you use a small model like a Llama 7B, and we can come in to replace it with a tiny model, less than 500 million parameters, but augment it with a hierarchical long-term memory. So that's actually even more impressive, 20X improvement on the memory usage and 3.4X improvement on energy efficiency. So that kind of shows you the model, the impact of model innovation. So the conclusion is that the long-term memory helps a lot. And by the way, I should also tell you the story. We were probably among the first ones using AMD GPUs to train multi-billion models. When we submitted a paper to a top AI conference 2.5 years ago, they have comments on technical contributions, and then this reviewer had a comment saying, it's refreshing to hear someone can use AMD GPUs to train large language models, and the community need alternative solutions. So you can see that the excitement was generated from this work, not only on the technical part, but the fact that we used this 4 AMD GPUs, MI200, as part of the donation from the HACC cluster. So it was a very impressive result at that time. So the second example I'm going to show you is the agent, because everyone's talking about the agent. And we are using these frontier models as agent. These models are crazy, trillion parameters, and you run them, and it costs you lots of tokens. But is that really necessary? Now our idea is that it's worthwhile to train small but highly customized models, agent models. So this is not easy to do, but it can be done. I can show you. If you want to train a specialized model, you care about the behavior cloning. You want to introduce some format penalty. For example, you want to make sure it can output actions, syncing pairs as you want. And you should have the right loss function. And finally, you do some parameter tuning. So that's actually the setup. I will not go into the details. On the right-hand side, to do optimization, there's a multidimensional problem. For example, you care about what's your advantage function designs, what is your importance sampling, right? And then what's your loss function, and you do dynamic filtering or not. But at the end, I want you to remember the result. We do have a very optimized policy, just published the last 2 weeks ago at ICML in Seoul. This is one of the top AI conferences that we can show that a number of tasks, the small model, 4 billion models, that for example, on the left-hand side, this is actually ALF world, and what it does is basically household planning. Your robots are run in that. 4 billion models, we outperform. You can see both the Gemini models and the GPT 5.2. So this is, again, paper published 2 weeks ago, but you submit 6 months ahead of time. So at that time, those are the frontier models you can have. On the right-hand side, that you can have an agent to do shopping for you. Most likely it's constrained shopping problem. You don't have an unlimited amount of money to shop, then you have a budget, and you have some preference. So if you look at that, again, we do, now our result, the scores. By the way, these are all standard benchmarks. You can look it up. And the 74% versus GPT, that 5.2, that's actually only 26%. So what it says is that you don't have to all the time call this trillion parameter models. You can be much more frugal, much more efficient if you know how to train, and then if you can spend the effort to customize. I think all of us do something special. We are not going to solve all the math problems, all the music problems in the world. So in my side, probably I care about the predicting circuit performance at the different levels. And some of you may actually maybe care about the creative writing, but there are certain tasks. So in that narrow domain, you can be 10 times, 100 times more efficient. So the second part I want to talk about is the platform customization. The first thing you can probably come to mind is that can we put this LLM on a customized chip? That do we really have to run on the general purpose CPUs, GPUs? A customized chip that is hard to do. At UCLA, in academic setting, we can easily do it on FPGA, which is a unique strength of AMD. Let me show you what we can do. By the way, we are pioneers in this space on deep learning on FPGAs. So this paper we published actually 2015. Now it's a FPGA Hall of Fame paper. But that was for AlexNet, that kind of a CNN network. You can see it's about 1.4 gigaflop operations and in that. But today you go to a Llama model that even fairly small size is very demanding. You are talking about the trillion, the T-flops, right? The teraflops operations, a difference of 1,000. So, and then the memory footprint is much, much larger. So how do you deal with that? There's multiple techniques to solve this problem. And I will show you two techniques. One is on quantization. The other one is on reconfiguration. Quantization, that you don't want to start with FP16, that you can, a lot of time you can come down. Because for a customized chip, if you can narrow the bit width, not only you save the memory transfer, you also reduce the size of your compute elements, right? Instead of do 8 by 8, that the logic to do multiplication you can do 4 by 4. However, if you do simple that post training quantization, or even do quantization aware training, that you get a pretty bad result. So here we make use of a work out of a Meta, that they do this basically a rotation-based quantization, that where you can, because what's known is that in large language model, there's a few channels which are very difficult to quantize because they're very sensitive to the output result, to the input and output. So however, if you do a Hartman transformation and basically do a matrix rotation in a new space, then things got separated out. And then with that, you can say also that's a lot of extra computation, but if we design our customized chip, it's not a big deal. Mathematically, you add a multiplication, and at the front end, you add another inverse transformation at the very end, but we can absorb all of them into that a new operation, a new matrix, right? So we do that, there's no increase in complexity. And so with that, we can get a much better PPT result, the PPL result, perplexity result. It's several X improvement. This is actually joint work with AMD together on the quantization side. But then another trick is that you look at your inferencing, there's two stages. One is pre-fill, right? You ask the question, what is AMD Advanced AI Conference? And then they will start answering. The second stage is called decode. Pre-fill, you can process in parallel all the tokens very easily. And so we have one configuration. And we find out if you do decode, it's a very different animal, that because you generate token one by one, and then every time you get a new token to process. So it's actually, you require a different configuration. So literally we need two chips, but with FPGA, we can just do dynamic reconfiguration. In about less than 0.3 seconds, we reload to get a new chip. You says whether 7.3 seconds is a problem or not. Remember, it's not, because let's say you get 1,000 tokens per second, it's already super fast. That's actually, if you want to output a few thousand tokens as the answers, and then, so this is a reasonable effort that overhead to pay. So with this, we had the highest frequency among all the implementations, and also the best energy efficiency, somewhere around 2 to 4x. But well, you may say, what's the use of such a small models? I mean, to customize chip design is challenging because it's a billion plus models, but for a large language model, it's small, right? But it turned out this will be ideal for something called the speculative decoding. I do not know how many people in the audience knows about this concept. So it's a beautiful setting where the token comes in, and you let a small model to do the job first, as much as possible, and it start doing decoding one by one, generate output for that. The small model sometimes is also called the student model, and then you have a more powerful target model, sometimes they call the teacher model, to verify. And you can say, you got 2 correct, and the rest is not correct. But then we'll start from there and keep going. So hopefully you get more correct, right? That not just 2. This is purely for illustration. So that's the basic technique. So the beauty is that doesn't matter how lousy your small model is, that I can guarantee the same decoding quality by adjusting the acceptance ratio on the target model. So this is exactly what we do. Probably it's a little bit difficult for you to see on this one, but the first line is you just do decode on GPUs and the whole inferencing on GPUs. That's the baseline. So we use a U80 FPGA, which is actually a fairly old FPGA, 16 nanometer process. But even with that, we can do actually 6x better in speed, and then I think 7x plus better on energy efficiency. And then if we project to a V80, which is a 7 nanometer FPGA, we can actually have a further improvement. It's over 7x faster and close to 8x better energy efficiency. So that kind of a heterogeneous setting is very, very useful. And then I want to give you the final example is on further heterogeneous inferencing between GPUs and FPGAs. So this is a fine-grained disaggregated inferencing. So DeepSeek, for example, some of these, there's a flurry of this release of fantastic open source models in the last few months. And for example, you take a look at what the DeepSeek offers. It's very, very complex. First, it's long context processing all the way to million parameters. And also, they introduce a lot of techniques. It's not simple, your K, V, and the query multiple attention. So they will actually prepare you into a manifold, all your input. And into this manifold, you start doing preparing your KV cache. But you're not going to do attention to everything in the KV cache. That can be up to 1 million tokens. So that's what's on the right-hand side. They have this concept called compressed sparse attention. That's where the efficiency comes in. So if you zoom in, by the way, this is not unique for DeepSeek. I just use it as an example. All the frontier model has something very similar. We do not see what the OpenAI or Anthropic offers, but we can see other open source models. So the idea is that you have a query comes in, and I need to eventually give you an output. And so there's actually a few steps. One is to just generate the memory. So what are the relevant information that I will get this KV cache generation? Then the second step is that you do some pre-processing. And then there's this whole memory processing pipeline. I'm going to show you what to do. And then finally is that you generate the output. So if you take a closer look of this memory processing pipeline, really there's 4 major steps. And one is to prepare the memory. And then the second thing is that for every elements in the memory, you want to compute the relevance scores. Is it worthwhile to do attention? And then once you have that score, you're going to do the retrieval to get the best K, maybe best 1,000, best 5,000, and then you do attention of that. So, so if you correspond to what's on the left-hand side, so that's actually the box is being shown on the DeepSeek model. So they have these 4 components. So I'd like to argue is that not everything in this pipeline are suitable for GPUs. You may say, how do you know? That in fact, I do not know, but we profile. So you can actually compute mathematically what's the opportunity. So one important thing is so-called the computational intensity or arithmetic intensity. You can see all these different stages. It varies from 1 to 200 plus, right? The higher the computation density is better for GPU because you bring in once, you do a whole bunch of a number crunching, and then you give it out. GPU is super powerful with that. And then if you do a little bit of computation, you come in, and then you cannot really, you have to put it out right away. That's actually a bad thing for GPU. You don't want to do that. You want to retain it in the memory and go to next stage, go to next stage. So that's called the data flow computation. So you need to have a mixture of a data parallel and a data flow computation. So that's exactly what we did. By the way, first I want to tell you this memory processing pipeline is the biggest deal in LLM inferencing. For example, the profiling we did with the DeepSeek 3.2 is that it's over 50% when you have long context. So this is a setup we have, and AMD is a unique company, has data parallel devices on GPUs and data flow devices on FPGA, so we use both of them. So this is how roughly it works. We have these two devices putting side by side, connected through a PCIe. I'll tell you the latency. So the input token comes in, and you will go to both devices, dense device and the data flow device. And then remember, I also talk about the preparing memories. So this is some kind of a projection that into some high dimensional space and or high dimensional manifold. So that's actually relatively friendly for GPU, so we'll put it there. And then the next thing you will find out is that this relevance computation and that top K computation. So that's actually not so friendly for GPUs. We do it on FPGAs, so data flow machines. And moreover, we fuse them. That's where the power of a data flow computation comes in, is that you do not access memory. You go from one stage to another stage to another stage. And then after we come back, you do attention. So that's perfect for GPUs. So this thing that will repeat and will come in another token. I can tell you the actual setup that on the dense device, we're using MI210. I know it's a kind of an old device. We're anxiously waiting to get the 350 device coming to the lab, and we have promised that will come any day now. On the right-hand side, it's actually a 55C device. Again, this is actually on a 16 nanometer, but again, there's a promise we're going to get we have the V80 just to get the shell working. So that's the cluster. We're very grateful for AMD for that HACC contribution, that donation. And this, that I want to show you, this actually, the communication is 7 microsecond. You say, is that high or low? It's actually not that bad, because think about it, if you do 1,000 tokens per second, so each token takes 1 millisecond. So this is actually 7 microseconds, so less than 1%, right? So it's something that we can justify, but the gain we have there is quite significant. So overall, we get the 1.2x that end-to-end speed up, and the 1.6% x energy efficiency gain. I think if we move on to the later FPGAs, the more recent FPGA, this is more significant. This is also just presented 2 weeks ago at the ICML. So I want to show you some that end-to-end result, how you use it. For example, some of you are probably coming from Fortune 500 companies. In the enterprise setting, you're not going to ask LLM all the time. So you most likely have a rack-based system working with data bricks. So you want to do queries on the relevant information in the company. How do you get relevant information? The first part is to do retrieval. Retrieval, again, you can do the computation. The computation density calculation is not very friendly for GPUs. So we do it on the FPGA. What's in the retrieval is that you do BM55, right? So that's one relevance metric. The other one is you do that vector, that search.
Thank you, Jason. It's been awesome. We're out of time for the session, unfortunately. But he is available just right after the session to talk and ask more questions. It was great learning. Small yet mighty, so let's learn more about it.